7 forces you can't see. 1 rule: we only trust what can be measured. No myths, no ancient aliens, no vibes. Each segment has a real experiment, a real detector, or a real astronomical signature behind it. If it sounds impossible, we investigate it. Dark matter is invisible to light, but not to gravity. One of the strongest signatures is gravitational lensing. Background galaxies appear stretched into arcs because mass warps spacetime. In clusters, the lensing strength often exceeds what visible matter can explain. That mismatch is why dark matter stays on the table. The bullet cluster became famous because different components separate during collision. Hot gas behaves differently than the dominant gravitational mass. NASA highlights this as one of the clearest examples where lensing maps don't line up with the ordinary matter distribution. You're watching gravity point to mass you can't see. Dark energy is the name for whatever drives the universe's accelerated expansion. NASA summarizes the key fact: expansion slowed at first, then later began speeding up, implying an unknown effect dominating on cosmic scales. That's the real part. The mystery part is we still don't know the physical identity of the driver. Here's the boundary line. We can measure the expansion history, but we can't directly capture dark energy as a particle or field in a lab. That's why it remains one of the biggest open questions in physics. The evidence is observational. The mechanism is still under investigation. Neutrinos barely interact with matter, which is why they pass through Earth like ghosts. But barely is not never. If you build a detector the size of a cubic kilometer and place it in quiet ice, rare interactions become measurable events. That's the logic behind IceCube. IceCube doesn't see neutrinos directly. It detects the secondary charged particles created when a neutrino finally hits something in the ice, producing Cherenkov light. That flash is the receipt, the invisible made visible by an engineered trap. Earth's magnetic field builds a magnetosphere, a protective system that deflects much solar and cosmic particle radiation. NASA notes it can change shape in response to incoming space weather, meaning it's a dynamic shield, not a static bubble. Auroras are one of the visible consequences of that invisible field. During storms, the magnetosphere is pushed and reshaped by solar wind, and particles are guided toward polar regions. That energy becomes light in the upper atmosphere. Aurora as a live readout of invisible magnetism. It's one of the cleanest you can't see it, but you can watch it work examples on Earth. Gravitational waves are ripples in space-time from violent events like black hole mergers. For decades they were theory. Then detectors became sensitive enough to measure the effect directly. This isn't light, it's geometry changing, and it can be recorded in hardware on Earth. LIGO's first detection, GW150914, was announced in 2016 and confirmed gravitational waves from colliding black holes. The key idea: LIGO measures tiny changes in distance as a wave passes through Earth. A century-old prediction became a recorded signal, the universe detected without a telescope. Quantum physics says vacuum isn't simple nothing. In certain controlled setups, you can measure forces that depend on an extremely small gap between uncharged plates. The shocking part isn't philosophy, it's repeatability. The vacuum can produce measurable effects when boundaries force fields into different modes. The Casimir effect is often cited as a clear demonstration. Change the plate separation, and the force changes in a predictable way. Interpretations differ, but the measurement itself is real, a tiny force that appears only at very small separations. Invisible fields leave a measurable push. Cosmic rays are high-energy particles arriving from space. When they strike the atmosphere, they generate extensive air showers, cascades of secondary particles spreading outward. You don't see the primary particle, but you can detect the shower it creates. Collision makes the invisible measurable. Ground arrays and high-altitude monitoring quantify cosmic ray showers by counting particle hits and timing coincidences across detectors. This is how researchers reconstruct energy and arrival direction without ever seeing the particle itself. Space sends the impact. Earth reads the footprint. Different domains, same logic. You don't need direct sight to prove reality. Gravity bends light. Expansion changes distances. Neutrinos leave flashes. Magnetism makes auroras. Spacetime ripples hit detectors. Vacuum gaps generate forces. Cosmic rays explode into showers. The invisible becomes real through repeatable signatures. Dark matter's identity remains unknown. Dark energy's physical nature remains unknown. Neutrinos still surprise us with their behavior. Space weather keeps testing the magnetosphere. Gravitational wave astronomy is still young. Quantum vacuum interpretations remain debated even when forces are measurable. Cosmic rays still hide their most extreme origins. These forces aren't just cosmic trivia. They affect radiation exposure at altitude, satellites, navigation systems, and the stability of Earth's space environment. Understanding the unseen is part of protecting the seen. The universe interacts with us whether we notice or not. 7 invisible forces. 7 independent chains of evidence. The universe is bigger than what light shows you, and every better detector makes reality expand. If it sounds impossible, we investigate it. Subscribe and join the investigation.